And he comes out winning, because most of the time the problem with these things is that the scientist is the one that ends up losing and looking ridiculous. And for that, in fact, he got a medal from the American Physical Society. In any case, it's more fun to listen to him. So you see, the talk is cosmology and science, question mark, from inflation to eternity. Thank you.
Thank you, Luis. Thank you. Thanks for everyone for showing up. It's a hot day. I thought people wouldn't come. Good. It's nice to be here in the Northern Hemisphere. So I'm going to, well, let's just start. I want to talk, basically, I like to give the sort of conclusions at the beginning, because that way you can nod off during the rest of the talk. So the good is that we're living in a golden era of cosmology, and it is true that observations are give us sort of a realistic chance of proving nature on scales that many of us would have thought a couple of decades ago at least would have been impossible to directly probe. The bad is that there are fundamental limits on science that are looming much larger than I think many of us would have thought they would have been, again, a decade ago. And the ugly is that it could be that these fundamental limits are changing, I would argue, the way we may do science. In fact, for many areas, for certain areas of science, we may lose our empirical handle on the universe, which would mean a dramatic shift in the way we try and answer questions. I don't think it would be the end of the ability to answer questions, but it would be a dramatic change. So I want to warn you that the end may be near. Okay, so this is a rough outline. I want to talk about four different areas. I want to talk about inflation and whether we can ever prove it actually happened, or whether we will continue to take it as an act of faith, as many people do, speaking of religion. And then I want to talk about physics as an environmental science, and our ignorance about all things dark, our continuous ignorance. And then I want to talk about how even falsifiable science can be false. So that's where we're heading in the long run. Okay. So, and the good thing is that it starts, it's sort of downhill. It'll get easier as we go on. So I want to talk about inflation, and I want to talk about the question of whether we can actually ever know if inflation happened. Inflation, of course, is a beautiful idea to understand basically everything we see in the universe, the flatness of the universe, the fact that the microwave background is isotropic, and we see these seeds of galaxies that are consistent with being produced by what are called adiabatic Gaussian density fluctuations. And you compare predictions of inflation with data, and it looks very good. But the question is, they're not really predictions, because, in fact, one could have presented different data that inflation would have been consistent with. In fact, the question is there data that inflation couldn't be consistent with? That's the important question. Is there something you can do to falsify inflation? Because consistency isn't really enough in physics. And so are there unique falsifiable predictions from inflation? And to talk about that, I just want to give you a mini 2-minute review of how inflation produces what we see, or is supposed to produce what we see. So this is actually maybe useful if you haven't seen it before, I hope. So the idea of inflation that is particularly attractive is that quantum fluctuations in the early universe become real physical classical density fluctuations now. And how does that happen? And the mechanism is really quite simple. It's often couched in a lot of formalism, but the mechanism is physically very simple. And I want to describe to you basically the physical mechanism. Inflation is a period of exponential expansion of the universe generally, because a quantum field gets stuck in some false vacuum, leaving a vacuum energy density that produces constant, and that causes the universe to accelerate. Now, what happens? Well, when the universe is exponentially expanding, it's in what's called a de Sitter space. And so the field has some vacuum expectation value, but there are quantum fluctuations about that expectation value. So at each point in space, the field is jittering back and forth. Now, just by dimensional analysis, the magnitude of those fluctuations, the only dimensional quantity in the problem is the scale of the vacuum energy, which determines the expansion rate and determines all the other parameters. So the scale of the vacuum fluctuations is proportional to a squared. Now, that's all you need to know to understand how inflation produces density fluctuations. Because if you have a perfectly flat potential here, perfectly flat, the field will just sit there in every point in space, and it's fluctuating. And in some region of space, it might fluctuate to the point of being on this part of the potential and fall down, and inflation would end. But in nearby regions, the field won't have fluctuated, and it'll still be in an inflationary phase. That means there'll be a density difference between those two places that's infinitely big. Because the region that's left inflation, the energy density will be redshifting, and the region that hasn't left inflation, the energy density will be constant. So the whole point, the reason quantum fluctuations produce density fluctuations, is that different regions of space leave inflation at different times. And as I say, if the potential is perfectly flat, then there's an infinite difference in times, basically, between different regions, and the density fluctuations are infinite. On the other hand, if the potential is not flat and very strongly sloped, the field is rolling down the hill classically, and then if one region jumps and leaves inflation, every other region is going to leave inflation very soon afterwards, because every region the field is rolling down. And so it is quite simple then that the magnitude of density classical density perturbations is just proportional to the scale of the fluctuation divided by phi dot, the rate at which the field is moving. If phi dot is 0, as I just said, the density fluctuations are infinite, because one region leaves inflation an infinite amount of time before all the other regions. If phi dot is very large, then the fluctuations go to 0, because all regions are classically rolling down this potential, and then the quantum fluctuations are kind of irrelevant. Every region leaves inflation at almost exactly the same time. So that's physically how quantum fluctuations get turned into density fluctuations and inflation. And as I say, the formalism is often daunting, but that's a physical argument. Well, that's one thing inflation produces. But the other thing inflation produces is gravitational waves. And it's exactly the same argument, but it's slightly different. Again, quantum fluctuations in de Sitter space of a scalar field are proportional to the expansion parameter, h squared. Now, the only thing you need to know is that the two helicity states of gravitational waves, each of them looks like a scalar field. It satisfies the equations for a scalar field in de Sitter space. Therefore, if there are fluctuations in scalar fields, there are fluctuations in the metric. And gravitational waves are produced just as those fluctuations. So in fact, in that case, the strain, as it's called in gravitational waves, is again directly proportional to h squared, and h squared by Einstein's equations is proportional to the fourth power of the mass scale associated with inflation. So the thing that's really important is that this is quite a generic prediction of inflation. As you can see, the scale of density perturbations depends upon the shape of the potential. But gravitational waves are produced simply by virtue of the fact that there's inflation at a given scale, and there are quantum fluctuations in the gravitational field. And so this is generic, and that's caused a lot of people to look at the possibility of detecting gravitational waves as a proof of the fact that there's might have been inflation. And I want to emphasize once again that tensor perturbations depend just on the scale of inflation, because we'll come back to that. So, a prediction of inflation happening is that there is a flat spectrum, because inflation keeps going on, and as long as it goes on, there are gravitational waves being produced, and they'll come back in the horizon at different times, and they'll always have the same magnitude given by the scale of inflation. So it's called a flat spectrum of tensor modes, and therefore, one might think that if you could search for gravitational waves, that would be a smoking gun of inflation. You can imagine other things that produce density fluctuations in the early universe, but this would be a sign of inflation. What's the signal? Well, one of the signals comes in the polarization of the cosmic microwave background. And that's particularly exciting because it might be measurable. And again, it's simple to understand. Here is an electron sitting in a bath of radiation. If the bath is uniform, the electron scatters the radiation uniformly in all directions. But now a gravitational wave comes by, and a gravitational wave scrunches up space in one direction and stretches it in another. When it does that, it will change the effective temperature of the radiation coming in this direction from that direction. And therefore, that change in temperature, that quadrupole change in temperature, will produce polarization because the electron will preferentially scatter the radiation in different directions. And you can convince yourself of this by thinking of some wave coming in and being scattered by an electron and going out. And you'll find that if the wave has a different intensity in different directions, you'll produce polarized radiation. And so polarization has been realized to be a potential key to search for gravitational waves from inflation. Now, how do we look for them? These gravitational waves are produced and inflation happens, they go outside the horizon and they remain constant, and then they come inside the horizon and like all radiation, they begin to redshift. So the dominant effect in the microwave background will be those waves that have just come inside the horizon at the time the microwave background is created. Okay? And the horizon size at the time the microwave background created is such that, in fact, if you expand the microwave background in spherical harmonics, it's a 200th spherical harmonic or so, which characterizes waves that are order the horizon size. So you might expect to see a signal on that scale, a polarization on that scale that's due to gravitational waves. Now, there is an interesting fact. If inflation occurs just by a simple scalar field, then the ratio of tensor modes to scalar modes is fixed. And the argument is, again, simple, so I'll give it, and then it's the most technical part of the talk, but it's pretty simple. If I have a scalar field, the energy density of the scalar field is just given by the 0,0 momentum, 0,0 term in the energy momentum tensor, and it's a half phi dot squared plus v, and the pressure term is a half phi dot squared minus v. And therefore, you can convince yourself relatively quickly that since the scalar density perturbations depend on h squared over phi dot, if you look at this, if you add rho plus p, the v's cancel and you get phi dot squared. Whereas the tensor piece just depends on h squared, you can convince yourself, it turns out, that the ratio of these things for a simple scalar field is the energy plus the pressure over the energy, which can be written as 1 plus p over rho. But p over rho is a very famous quantity nowadays. It's called the equation of state. If you have a cosmological constant or a perfect de Sitter phase, the equation of state is such that p is equal to minus rho. So this becomes 1 plus minus 1, and it's 0. And so the difference between being in a perfectly de Sitter phase and the actual state we can call epsilon, and that will give this ratio. Now, the interesting thing about this ratio is it completely distorts what's true. This is the standard ratio that's used in the literature, but it's exactly the wrong thing to do. This makes it appear as if this ratio is insensitive to the scale of inflation, but it's not. And the reason is, it's the wrong way to write this. The term that depends on the potential is in the denominator, whereas the term that's independent potential is in the numerator, and that's the wrong way to write things. Because remember, so for a perfectly flat potential, R is 0 because W is minus 1. You live in a de Sitter space. But what does that really mean? What it really means is S is infinite. The scale, T, the amount of tensor perturbations that are coming is just proportional to the scale. It's fixed. And in a flat potential, S goes to infinity. And so it really does depend on the scale of the potential, even though in this way it looks like it doesn't. And so if we can measure this ratio of tensor to scalar modes, we know not just that inflation happened in principle, but the scale at which it happened, and perhaps if it happened at the grand unified scale. Now, the interesting thing is we have a handle on this, because scalar density perturbations also depend on the scale of inflation, and they're measured. We've measured delta rho over rho, and it's 10 to the minus 5. That's the temperature fluctuations in the microwave background. It's given by this, rho over this quantity. Now, therefore, the mass scale of inflation, which is the fourth root of the energy density, which is the fourth root of the potential, if you just look at this, is therefore given by 10 to the minus 5 halves times this. And this, no matter how close this is to minus 1, the fourth root of this is about 1. So we know the mass scale of inflation by measuring if inflation is responsible for the density fluctuations we see today. The mass scale is 10 to the minus 3 in units of the Planck scale, which is very exciting for particle physics, because that's about 10 to the 16th GeV, which is comparable to the scale we think grand unification occurs at. So that's very exciting. And in fact, therefore, we can write this down as being that the scale of inflation, the fourth root of the potential, is 10 to the 16th GeV times this quantity r over 0.01 to the 1/4 power. So 0.01 is the fiducial value. If r is 1/100th of the ratio of tensor perturbations measured in polarization compared to scalar density perturbations is 1%, that corresponds to a scale of 10 to the 16th GeV, which is what we sort of expect it to be. So this would then say that we would expect to see large, and by large I mean 1% effects, which might be measurable in the next generation of experiments. So people have proposed, as a result of this, building a satellite to look for polarization from the microwave background as a way of measuring, and it's been called an inflation probe. If we can measure a polarization bigger than 1%, we should be able to see the gravitational waves from inflation, and this argument suggests they should be there. So this is a schematic, and it's a $1 billion satellite, because that's the unit in which satellites come. It used to be a lot of money in the old days. So people have proposed $1 billion satellite to look for inflation, and I would argue that it's in fact a very good idea, but for reasons that are different than people would suggest, as I'll show you. Now, the question is this really a smoking gun? Do we really expect large tensor perturbations? I gave you an argument that seems unimpeachable. If you have a scalar field, we've measured the scalar density perturbations, and therefore we should know that r is bigger than 1%. But there's another argument that tells us that in fact r should be very small. Because during inflation, the field is fluctuating and rolling, and we can calculate how far it rolls during inflation. And the amount it rolls compared to the Planck mass is 1 times r over 0.01. So what that really means is if the r is bigger than 1%, during inflation, the field is rolled by an amount more than the Planck scale. It has a value bigger than the Planck scale. But that really means we should be suspicious. Because the minute the field has rolled more than the Planck scale, quantum field theory calculations are suspicious. Because it breaks down. And therefore, you might not believe anything. Okay? In fact, you might argue, as is originally the case, that string theory would argue that in fact it wouldn't be allowed at all. Because in many versions of string theory, the field that is rolling is related to the size of an extra dimension in string theory, and those extra dimensions typically have ordered the Planck scale. So the field couldn't, it used to be said that the field could not roll more than the Planck scale because that was the size of the dimension. Therefore, it was a theorem that r had to be much smaller than 0.01 if string theory was correct. Now, in fact, string theorists would argue that if we're going to talk about super Planck scale excursions, you need string theory because it is the only UV complete theory in which you can calculate anything possible. There's another way of thinking about that. In string theory, anything is possible. And what has been realized more recently is that this argument is, in fact, as you might expect, is infinitely malleable, as string theory is infinitely malleable. And in fact, it turns out the prediction is that r can be absolutely anything, which is the same as everything else in string theory. So, what we know is that we don't know anything, which is good, I suppose. I think I'll skip this. It's too hot for me to go into this. Okay, so I want to now ask the more interesting question. It doesn't really matter what theorists think. As I pointed out, some theorists think r is large, some people think r is small, but what really matters is experiment, because that really determines the answer. So let's say we measure in the next satellite, or in the Planck satellite even, a polarization of the microwave background. Will we have discovered inflation? Because that's what is often claimed. I want to point out that when you argue that you have a smoking gun, you have to be very careful that you really do. in a murder trial or in physics. And I want to point out an example of the fact, a straw man, to point out that, in fact, I would argue that anything that happens in the universe at early times will produce a signal that is identical to that from inflation. And the simplest example I want to give you is a simple example that I thought of about 20 years ago almost. Just to give you a straw man to think about. Let's imagine that after inflation, say, there's some global phase transition. A scalar field has a phase transition. There are lots of phase transitions happening in the universe. What does that mean? Well, it means at different horizon volumes, the field takes different values. This is a well-known argument, and depending upon the topology of the field, this is what produced magnetic monopoles originally. But forget about topological obstructions. Causality tells us that the field will take different values in different regions. That will produce gravitational waves. Because as the horizon grows, you see, this will mean that on scales larger than the horizon, there are gradients in the field. Gradients in the field mean you're storing energy. But when the horizon grows, the field will line up. That's what it does. But when the field lines up, those density gradients will go away. You'll have a changing energy density. And general relativity tells us that if the energy density is changing and it's not spherical, you'll produce gravitational waves. It's a simple argument, and the overall, because of the dimensions of the problem, the gradients are proportional to two quantities. The scale at which the universe is expanding at the time, the horizon size, and the scale of the vacuum expectation value of the field. And you could do a simple order of magnitude calculation. So this means at all times, in this model, let me make this clear, at all times gravitational waves are being generated. The phase transition may have happened at 10 to the minus 30 seconds after the Big Bang, but today gravitational waves are being generated on our horizon because our horizon is growing and different regions are coming into contact, and on the scale of our horizon, gravitational waves are being generated. And you can do a calculation, it doesn't matter, it's a back of the envelope calculation, that says that the strain is proportional to the scale of the field over the Planck mass squared. Namely, it looks identical to that of inflation. Inflation would have had the h here, the expansion factor. It's a flat spectrum of gravitational waves on order of the horizon, and it looks identical to that due to inflation. And so, as I say, 20 years ago, I did this back of the envelope calculation, and I said, the key quantity is, what's F? What's this, that's something that depends on the specifics of the transition, and I assumed maybe F was a tenth or something. And I didn't worry about it, because it was totally unobservable. But now we're at a point where some people are about to try and spend $1 billion, potentially, on a satellite to look for this stuff. And it might be worthwhile seeing what F is. So we redid this calculation recently we tried to find an analytical model where you could actually calculate things. And for field theory, analytic models where you can calculate things are what are called the large N limits. So I don't want to go into the details of this, but we found a model, a large N ON model, which, by the way, does not have topological defects, where you can calculate things exactly. And the result was surprising. In fact, it's the first time in my own life where dimensional analysis has failed in one way. We confirmed the result that you have a flat spectrum of gravitational waves, but the value for F was not the value I thought of maybe a tenth or one. The value, in fact, was 2,000. A dimensionless parameter of order 2,000. Now, where does that come from? Well, there are a lot of 8 pi's in gravity. And in fact, in this case, all of the 8 pi's and everything went in the same direction. I've never seen it before. But it was 4 orders of magnitude larger than I had imagined. This suggests that if you look at the ratio of strengths of gravitational waves produced by inflation happening at some scale h, or some phase transition that happens at a later time, the ratio has a prefactor of 10 to the 4th, and then the ratio of scales. Now, I should say there's a group here, in fact, at Geneva, that has argued that the prefactor is not 10 to the 4th, but 200. I'm not convinced I believe them, in fact, but it doesn't really matter. The factor is much bigger than 1. And this means that you could have, after inflation, a phase transition that would, in fact, produce gravitational waves which would overwhelm the signal due to inflation. and would look identical in principle. Or would they? We don't know. It turns out that this is the way that this is what the spectrum looks like. One is of order when p tau is here, this is what's called conformal time. When that's order 1, that's the horizon size. And the difference between this spectrum and that from inflation is that when p tau is less than 1, you're outside the horizon. And inflation, the spectrum is flat outside the horizon and then falls off as waves redshift. In our case, it's peaked and then it falls off outside the horizon, but it's continually generated so that any time it always has the same value. Now, is the difference observable? The answer is we don't know, because in fact the main signal that comes from inflation is precisely those waves of order the horizon size. Now this is dying maybe, so we'll see if okay. So we don't know if it looks any different. And we're now trying to calculate things. What's been recently suggested by Zaldariega and Baumann is that there may be a way to tell this, because to really look for inflation. Because in inflation, the waves get pushed outside the horizon and everything is fluctuating. There's coherence in the waves outside the horizon. In this model, there's incoherence. The waves are generated incoherently. And maybe that gives you a signal. They've argued the horizon size is of order a degree or two, and maybe I'll use your old-fashioned pointer. I hate this. Where do you press it? I think it's been 20 years since I've used this, and it still looks the same. Okay. It's okay. Anyway, and so maybe there's some signal, and I'm not going to go into it. It's too hot here again. But the answer is I don't know, because it turns out in our case there are also super horizon modes. And so the bottom line is we don't know that there's any way to distinguish. Even if we see polarization, we may not know it's due to inflation. And therefore, there may be no unambiguous predictions that tell us inflation happened. We may just have a fact that inflation is consistent with everything we see, and we may have to say if it walks like a duck and quacks like a duck, it's a duck. But we shouldn't, on the other hand, be I don't want to suggest that I didn't come here to bury inflation nor to praise it, but measuring R is important. It's not quite like measuring, right now and at places like the Tevatron or where other places, or that we're constraining supersymmetry, and it's this huge parameter space, and each time you do a new experiment, until you see something, you're constraining some region of parameter space. But unless you're a theorist, one region of parameter space is essentially the same as every other region. The only regions that look special to theorists are for their models, but to every other theorist, it doesn't look very special. But this is very different, because if it is worthwhile measuring this, because if we measure R at the level of 1%, if we don't see tensor modes, it will give strong evidence perhaps, and it'll tell us that inflation couldn't have happened from a simple scalar field. That maybe indeed we have to incorporate the ideas of string theory. Okay? And so it really will tell us, if we can measure it at that level and we don't see anything, it really will basically say inflation cannot be simple and the kind of thing that everyone predicts. And it means that we're going to have to understand quantum gravity. But the other thing I want to point out is that even though this is bad for inflation, it's good for physics. Because this calculation, because of this factor 2000, tells us that tensor modes are produced much more efficiently in the early universe than you would have imagined otherwise. And it really means we have a much better lever arm. A lever arm that's 2,000 times more efficient than we might have thought before. So in fact, even if it's not inflation, we may be able to probe physics at the gut scale more effectively than we thought before by looking for gravitational waves. So while the ability to prove inflation goes away, it's interesting. And so we may have to give up falsifiability for inflation. We may never be able to find anything that unambiguously tells us inflation happened, but we still may think we're doing good physics. We're going to be probing the universe at new scales. Okay, that's as good as it gets. It's going to go downhill now. Because as difficult as it is to probe inflation, I would argue that it's infinitely more, or not infinitely, but much more difficult to probe dark energy, dark energy is the buzzword nowadays. And in fact, while an inflation probe has not been approved, as you know, in the United States at least, it was argued that the next $1 billion we spend on a satellite should go to measure dark energy, because dark energy is the biggest puzzle in physics. And it is. But the question is, will we learn anything? And I would argue the answer is going to be no. We're not going to, I don't think we're going to get an empirical handle that's any different than anything we have nowadays. So here's the point. The only interesting question having to do with dark energy is it different from a cosmological constant? That is the only thing that's going to give us information from a fundamental particle physics perspective. And really that means, is the equation of state of dark energy -1, that of a cosmological constant? Well, if it is -1, it doesn't tell us anything. The only way we'll learn something is if it isn't -1. Because if it is -1, it's consistent with a cosmological constant, but it's consistent with any other sensible idea, essentially. A scalar field stuck and about to have a phase transition will be -1. So the only way we'll learn something we don't know now is if it isn't -1. And I would argue, in fact, that basically the most sensible theoretical prediction is -1. Because, in fact, every quantum field theory, except a conformal field theory, every quantum field theory predicts vacuum energy. It predicts the wrong value by 120 orders of magnitude, but it predicts, you can't get away from that. So it wouldn't be surprising if, in fact, there was a vacuum energy. Moreover, the bad news is that observations already suggest W as -1. If they were pointing towards a different value, we might have hope. But this makes it much more difficult to answer the question we care about, namely, is it measurably different than -1? And if we measure things with a factor of 2 or 3 better, and we still find it's approximately equal to -1, we will have learned precisely nothing. And that, I would argue, is our future. We will spend $1 billion, as we should, and look for this quantity and hope to measure something, and we will find we haven't learned anything. The problem is, as I say, you can look at what the numbers are now, and everything is converging on W being -1, as you can see. Now, in fact, there's a better way of putting this. The problem is the following. Depending upon who you are, this is the current limits of W, -1.2 to -0.8. So it's centered on -1. How much better can we do? The point is that because it's centered on -1, if we reduce these error bars by a factor of 3, at 2 sigma, W's got to be, fairly far away from, if W is -0.95, because you're so close to -1 already, you have to reduce the error bars by a large amount to say with direct confidence at 3 or 4 sigma that you're not in a cosmological constant dominated universe. And it's worse because, in fact, this is not the right way to talk about things. Because we don't have any idea of of a theory of W. If it's not a cosmological constant, then W could vary with redshift. And there's while people have models, there's no convergence on what W should do as a function of redshift. So assuming W is a constant is not a valid thing to do. And once you allow W to vary with redshift, your ability to constrain W gets much worse. And we've actually looked at this and tried to find model-independent ways of constraining W, and I was going to go through the details of this, but details are irrelevant at this point because the data is such that it's very bad. Here, for example, if you allow W to vary, so here's -1, and you allow it to have a first derivative as a function of redshift, this is what you'll be able to do if you measure, well, this was called SNAP, it's now called a dark energy probe, but it's basically the same. If you measure 3,000 supernovae, once you allow this extra degree of freedom for variation in redshift, your ability to constrain W goes out the window. And if you look at what you can do here, after 3,000 supernovae and $1 billion, even if you can measure supernovae with a redshift accuracy that's better than in any current survey, the uncertainty in W will be almost exactly what we have now. And it gets worse, by the way, if you allow a redshift uncertainty in the measurement of supernovae, or if you allow supernovae to be measured with an accuracy of what we measure now, or if you allow them to get worse with redshift, it just gets worse. And so it's going to be extremely difficult to actually measure W, and in fact I would argue that it's quite unlikely in the lifetime of anyone in this room that we'll have empirical evidence that W is not -1. And that is unfortunate because that means we'll need a good idea. And that's much harder to come by than a good experiment, okay? Because you can't predict when a good idea is going to happen. And so, in the interim, there are a lot of bad ideas. And I want to talk about one that has caught a lot of people's attention. It may not be a bad idea, it might be right. It's just depressing. The fact that there is dark energy in the universe has driven many people to ask interesting metaphysical questions. And here is one. Here's a brief history of time. This is the history of the universe. This is the density of matter as the universe expands. Its density goes down as 1 over the volume. The energy density of empty space, if it's a cosmological constant, is constant. And this is where we live now, where the cosmological constant or the dark energy is about a factor of 2 bigger than that due to matter. Now there's something that's obvious when you look at this plot. We are living at the only time in the history of the universe when those two numbers are about the same. At all earlier times, the density of matter is much bigger than the energy density of empty space. At all later times, the energy density of empty space is much bigger than that of matter. Why should we be living at the time when those two numbers are the same? Why, 14 billion years after the Big Bang, at some random time, should we be living at such a unique moment? It violates the Copernican principle. It violates all our ideas about not being at a special time in the history of the universe, because we appear to be at a very special time. So an argument has been given for why this may be the case. And the argument is quite simple. Galaxies exist. How does that solve the problem? Well, it's quite simple. Let's assume the vacuum energy density were 50 times bigger. Then these two curves will cross at a different time. In this case, they'd cross at a time when galaxies first formed. But vacuum energy density is gravitationally repulsive. So if it dominated over matter, when galaxies first formed, the repulsive force would have dominated over the attractive force, and galaxies never would have formed. So the argument is that if this value were much bigger than the value we see today, galaxies would not have formed. That has caused people to say maybe this is significant, and produce what I call anthropic mania. It is the following. If there are many different universes, and the energy of empty space can vary in each one, then only those in which it's not much greater than what we measure will galaxies form, and only then will stars and planets form, and only then will astronomers form. So the value has the value it has because astronomers have measured it. That's the argument. It sounds like a tautology, but it's not quite a tautology. Because it's really just a case of natural selection in a cosmic sense. Bees can detect the color of flowers to get honey because if they couldn't, they wouldn't survive. We live in a universe that has a cosmological constant that allows us to live because if it didn't, we wouldn't live in the universe. So it has potentially some content, but it's very depressing because it flies in the face of 450 years of successful physics. We used to want to explain why the universe had to be the way it is, not why it should generically be different. Okay? Now I want to spend a little longer trashing this, but let me just say that particle physicists, many of them, have found this incredibly heartening. Because in cosmology there's really one thing you don't understand, which is dark energy. But as we all know, in particle physics, there's many more things we don't understand, and we haven't understood them for much longer. Many of the parameters of the standard model have been a mystery, right? That's what we want to hopefully discover at the LHC. Why is gravity the weakest force in nature? Why is the proton 2,000 times heavier than the electron? Why there are 3 generations? All these fundamental questions that we've had for a long time. And some people have said, this is great, because maybe we don't have to answer any of them. Maybe not only is the cosmological constant just a historical accident, maybe every parameter of the standard model is a historical accident. Physics is completely environmental science. There's no fundamental theory. In fact, instead of a theory of everything, what you need is a theory of anything. And of course we have such a theory. It's called string theory. And like everything in string theory, warts become beauty marks. And so, as you all know, string theory originally was hoped in the early days would provide a unique description of our universe, but as pointed out, in fact, because of the fact that generically string theory requires a lot of extra dimensions which have to compactify, different ways of compactifying will produce different physics on large scales. And it's been argued that there are perhaps 10 to the 500 different ways of compactifying the extra dimensions, producing 10 to the 500 different possible universes, and that used to be thought of as a negative. But you see, now it's been a positive, and it's gotten a new name. It's called the landscape. Because if every way you compactify these higher dimensions produces a different four-dimensional universe, in every different four-dimensional universe there may be a different vacuum energy. And then string theory will predict universes with every possible vacuum energy, and one of them is bound to be the one we measure. Now the question is this science? We don't know. The sad thing, I have to say, is it may be true. I mean, it's as plausible, in fact, it's probably, right now, the only, this anthropic argument right now is the only, is the most plausible of the arguments for why the cosmological constant has the value it has. And if it is, it really means that physics is quite different than we used to think. And the problem with this is that we only have a sample of one. If our universe is a statistical outlier, but we only measure one point, it's a problem. I mean, physics becomes like medicine, right? Where samples have two people in them and stuff. Now, before you get too excited about anthropics, I do want to point out some of the problems. First of all, it is an idea based on ignorance. Namely, it's based on not knowing the fundamental physics. So we don't have the slightest idea. It's suggestive at best. It never is compelling. It's not like calculating G minus 2 in quantum electrodynamics, okay, where the answer is compelling. It's suggestive because we don't know the fundamental physics and we're just making probability arguments. But probability arguments in a case where we don't have any idea of the phase space involved. We don't know what variables are anthropically selected. For example, if the cosmological constant is the only thing that varies in universes, you come up with a very different answer than if you allow other variables to change, like the density fluctuations or the mass of the proton or anything else. We don't even know the set of possibilities because we don't know all the parameters in physics. And as I say, it's never compelling, it's only suggestive, but for those people who are young, which is nowadays more people than me, most of the people that are younger than me, it's been used before. Almost, if you look at the 20th century, almost every time a fundamental quantity came up that it didn't appear to be sensible, people invoked the anthropic principle. There are many examples having to do with stellar evolution, and for example, and nuclear physics. And every other time it's been applied, it's been wrong. That does not mean it's wrong now, but you should be wary. But the real big problem with the anthropic principle is the following. The results depend completely on your choice of initial conditions. For example, if you assume your initial conditions are such that the universe has to produce George Bush, heaven forbid, then you'll come up with a very different set of predictions for your fundamental parameters than a better universe which didn't produce George Bush. And therefore, we know that if our conclusions depend upon our initial assumptions, and we don't have any way to constrain our initial assumptions, it's not so clear that we're doing physics. But the final thing I want to do before I leave this to trash it is that I don't believe the anthropic principle can ever explain a cosmological constant. All it can ever do at its best, as it's currently framed usually, is just demonstrate correlations. Namely, the argument I gave you about galaxies gives a correlation. It says that there's a correlation between a value of the dark energy, the value of the energy of empty space, and our existence in galaxies like we see nowadays. So people like us are correlated to the existence of a dark energy of the value we see. But that doesn't explain anything, because we have no idea if we're typical observers. Correlations mean nothing in science unless you have an underlying physical principle that explains the correlation. I'll give you an example, again for people of my age. Take the solar neutrino flux in Ray Davis's experiment over 25 years. As is well known, the flux in that experiment was extremely highly correlated to the value of the US stock market. The correlation coefficient was better than 0.95. Few people, actually no one that I know of actually wrote a paper suggesting that there was a relationship. It's the big problem that occurs, again, just since I can trash doctors here, in many fields of psychology, for example. Correlations don't mean anything unless you have an underlying physical principle. So the fact that there's a correlation between our existence and a value of the cosmological constant doesn't mean it explains it, because we have no idea if we're typical observers, and we don't know the phase space of typical observers. And I could give it, I had a numerical argument for this, but again, I figured late in the afternoon I wouldn't give it, and I'm happy to give it if you have questions. Because I want to move, oh, I guess I did. Well, but I'm not going to do it. I'm too tired. I'm happy to give it to you, but we've written a paper showing that even if you can show that there's a probability of order unity, that we exist only if the cosmological constant has the value it has, for most of phase space, life will exist with a very different cosmological constant, and it just assumes typicality. So bottom line is, in order to solve this problem, I don't think we'll have an empirical answer. I don't think experiment will tell us, not experiment, observation will tell us anything. Observation was great for discovering dark energy. It will be crummy for constraining it. And since we can't do experiments on dark energy, at least no one's come up with anything we can do in a laboratory that allows us to measure it, we don't have the empirical physics handle that allow us to do anything. So we'll require pure theory, and that means we're betting on the future and some bright idea that someone may have. And as I want to conclude in the last part of the talk, the future is going to be a lot worse. So I want to end the optimistic part of the talk and talk about the extremely far future. I want to point out that falsifiable science is pretty good, but it itself has its problems. And I want to talk about I want to recall the universe around 1900, or just before or around the time Einstein invented general relativity. The conventional wisdom among scientists was that the universe was static and eternal. And in fact, we lived in a galaxy, in a universe that was otherwise empty. In fact, de Sitter wrote down a metric for that universe, which looked like a static universe, but it was the wrong coordinates, which described precisely that, an empty universe that was static. And that's the universe that Einstein thought we lived in 1915. Now, of course, we've learned that the universe isn't static, and we've learned about the Hubble expansion, we've learned about the Big Bang, and those have been the great successes of 20th century physics. What I want to ask is, what will the future bring? And by the future, I don't mean next year or next decade, I mean in a long time. In particular, the remarkable thing about a universe dominated by a cosmological constant is that the longer we wait, the less we will see. Because the universe is accelerating. And in a finite time, every galaxy outside of our own local cluster of galaxies will be moving away from us at the speed of light. Because the universe is accelerating. In fact, it will be moving away from us faster than the speed of light. And we can calculate this, and we did this a long time ago in the 1990s, we calculated that in fact in a time frame of about 100 billion to 1 trillion years, which may seem like a long time, although not long compared to this talk perhaps, but a long time, it's not long in a cosmic sense, because the longest main sequence stars, the longest lived main sequence stars are about 10 trillion years old. So in 100 billion to 1 trillion years, you will expect stars just like our sun to exist, more or less, and planets around those stars that are powered by solar power, and astronomers that build instruments and experimentalists that do experiments. And what will they come up with? Well, what they will come up with is a universe that, I would argue, is precisely wrong. They'll do the best physics they can do, and they'll come up with exactly the wrong answer. They'll come up with the answer that we thought the universe was in 1900. Why? Let me go. I will argue that every single piece of data that tells us there was a Big Bang will disappear. The first bit of data that will disappear is the Hubble expansion. Hubble's great discovery in 1929, the universe is expanding, was based on looking at galaxies and the motion of galaxies. But in 100 billion years or so, to 1 trillion years, there will be no galaxies. Every galaxy outside of our own will have disappeared. It'll be moving away from us faster than the speed of light, and will therefore be invisible. So the only galaxy we can see it'll be a meta-galaxy. Our local cluster will collide together and form a big galaxy. There'll be one galaxy, observable galaxy in the universe, and there'll be no Hubble expansion. Interestingly enough, all evidence for dark energy will disappear. Because even though at the time when the universe is 1 trillion years old, the density of matter compared to the density of dark energy will be 1 part in a million million, dark energy will be a million times more abundant than matter, all evidence for it will have disappeared. In fact, if you think about when you can measure dark energy, there's only one time, today. Because when dark energy has a value, energy density much less than that of matter, it doesn't affect the expansion rate of the universe, so you can't measure it. When it's much bigger than that of matter, it's driven all the matter away. So we are living in the only time in the history of the universe when you can measure dark energy. But it gets worse. You might say, well, look, we've got a lot of evidence for the Big Bang. What about the microwave background? The great discoveries, 2 Nobel Prizes already for the cosmic microwave background. It's really the afterglow of the Big Bang. Well, it goes away too. First of all, as the universe expands, we all know the temperature decreases, and in fact, when the universe is 100 gig years old, the intensity of the microwave background will be down by 12 orders of magnitude. But that isn't a problem. Maybe experimentalists will be 12 orders of magnitude smarter. That is imaginable. But it doesn't matter, because the galaxy has free electrons in it. And in fact, if you calculate the free electron density, you can calculate the plasma frequency in the galaxy. And you will find that when the universe is 50 times its present age, the microwave background frequencies will all be below the plasma frequency, essentially, and the microwave background will not permeate the galaxy. So no matter how good an experimenter you are, there's nothing to see. So let's see, the Hubble expansion, the microwave background is gone. What else? Well, in fact, you might recall Lemaitre. The first evidence for the Big Bang wasn't observational in a sense. It was from Lemaitre, who argued, in fact, that the solution of Einstein's equations required a Big Bang. But that was the solution that Einstein's equations for a universe of uniform density. In fact, a universe that's empty, except for a single mass, has a nice other solution to Einstein's equations, a Schwarzschild solution, where the mass will eventually collapse into a black hole. So general relativity in its static universe does not require a Big Bang at all. Okay? I want to point out that the physicists in the far future will discover general relativity. They'll do local tests. They'll discover quantum electrodynamics. They'll discover electromagnetism. They'll discover everything we've discovered about physics. And they'll do the best observations they can do, and they will come up with completely the wrong answer. The last sort of pillar of the Big Bang is the primordial abundance of elements. That's the other thing that tells us there was a Big Bang. But it'll go away too, because here's this beautiful picture we have now that tells us, all the elements, the hydrogen, helium, lithium, deuterium, are consistent with the Big Bang. But in particular, helium is 24%. But when the universe is 1 trillion years old, far more helium will have been produced by stars than was produced in the Big Bang. The abundance of helium will be 60%. And in fact, all evidence of primordial produced helium will have gone away. All the helium that's observed in the universe could have been produced in stars without a Big Bang. So, and in fact, the only way we can measure deuterium right now is by looking at absorption from quasars, but there won't be any quasars to look for absorption from. So, the future will return to the past. The picture that these physicists will come up with, which is falsifiable because every test you can perform will be consistent with a picture which is identical to the picture we had in 1900. They will ascertain by their best observations and their best theory that they live in an empty universe that is static. And there won't be a single experimental observation you could perform that will tell you anything else. So to end with the good news, we live in a very special time. The only time when we can observationally verify that we live in a very special time. I hope you catch the facetiousness of my remark, because this suggests something unusual, a cosmic humility. Because we have come up with this very consistent picture of the universe, none of which we understand. A cockamamie universe that's flat, dominated by a cosmological constant or something very much like it. And everything fits. Every piece of data fits with that picture. But had we evolved, and I can say that since I'm not in the United States, had we evolved 5 billion years ago, maybe we would have been able to measure observables we can't measure now that would give us a very different picture. Or maybe 50 billion years from now, there'll be other observables that will tell us something else. So before we assume our picture, which is in principle falsifiable, is complete, we should take this example. And in fact, the future really is the following. We will be lonely and ignorant, but dominant. And those of us who live in the United States are very used to that, so thank you very much. Thank you. Okay.
Well, Alvaro has a question, and then Gia.
Why am I not surprised?
Because you put so much philosophy into your talk,
Yes.
that it is difficult not to disagree with at least 50%.
How much of it?
At least 50%.
Oh, okay. Well, that's better than I thought. Okay.
Let me give you some practical examples.
Okay.
One of them is you say it's not worth $1 billion
Oh.
to check whether...
No, it's worth. No. Let me make. I absolutely think it's worth spending $1 billion. I think observers and experimentalists should spend the next 20 years looking for this, because maybe we're wrong. But they should do it, because I don't want to do it. But they should do it, and we should spend the money. But I would bet my house, and I already have, although it's worth a lot less than it used to be, that they won't see anything. But we have to do it because we never know the answer. It's just they should waste their time.
That's essentially what I was going to say. You won't know the answer unless you look for it.
Oh, we have to do the experiments because maybe we're wrong. But we have to be prepared for the fact that we may not be. And that's all I'm saying. I would right now suggest, based on what we can measure, if we're realistic about systematic and statistical uncertainties, that it's going to be extremely difficult to come up with something that's going to tell us. But I agree with you completely, Alvaro, that we should do the observation and the experiment anyway, because you never know.
The other example I want to give more is that in 1 trillion years, I will definitely have found a way to measure the cosmological constant locally.
I don't know how to interpret that, Alvaro. I hope you're around in 1 trillion years to do that. It would be remarkable and interesting. Let me just say that there would be very little motivation for it. I think I can give. Let me be simpler. Let me give you an experiment that you don't need to do it locally. Here's an experiment that would allow us to measure the cosmological constant 1 trillion years from now. Just create an object with the luminosity of a supernova and send it on a trajectory to escape our galaxy and wait 10 billion years and then observe it to begin to accelerate. Right? That's an experiment that would do it. The question is whether in my, if I think of the National Science Foundation of my country, could you motivate such a big experiment? Even if you could do it, a 10 billion year old experiment. The point is, there's no motivation for it because every other bit of data is completely consistent with something else. So why would you develop such an incredibly expensive experiment to look for something for which there was no evidence whatsoever? You'd have to convince the funding agencies that there was a good reason to do it. Maybe it'll do it. But I want to remind you that if the cosmological constant has the value we have, it corresponds to a temperature, a Hawking temperature of about 10 to the minus 45 degrees Kelvin. And it may be very difficult to argue that you should justify, that even if you see some effect at that level, some additional noise, that is due to something that is otherwise completely unmotivated. But yeah, it's great. I agree. We should continue to work and think and think about this because it's the only hope we have. The other suggestion I've made is that we should send out cosmic beacons right now. We owe it to future civilizations to send out large objects outside of our galaxies that are moving so that they can serve as markers for the future. But I haven't actually written that up because I think it's ridiculous.
Yeah, so my question is probably related with this last thing you said because you can always discover that you are in the Sitter space by measuring very precisely precession, anomalous precession because you can tell the difference between Schwarzschild de Sitter and just Schwarzschild. And
Well-
then you can just...
Well, hold on,
Then you continue it back, repeat Big Bang.
hold on. What? Yeah, where are you going to measure this?
Oh, the solar system is enough.
Well, yeah, but I think you can. I think it's very. I think the answer is you can't. I mean, because you're right. It produces a. The question is, you're going to have to know if you see a small deviation from precession. You have to know that you have to know exactly what all the masses are that could give an effect that's comparable. Remember, I mean, on the scale of our solar system, right now the effect of dark energy is unmeasurable, right? By a huge order of magnitude.
But you have like if you have trillion years to go with the statistics. No, actually, even the current statistics is surprisingly good.
Well, let me.
In fact, one of the in fact there are experiments like these lunar ranging experiments.
No, I agree with you. Look, there may be anomalies one might be able to imagine. It's hard for me to imagine that those anomalies would not be more easily explained by a small mass distribution that you didn't know.
No,
for example, let's think about the Voyager anomaly right now. Okay?
But that's one thing, and what I'm saying is that you can measure, you have a huge number of planetary systems, and you can do precision astronomy, and I think it's almost unimaginable that you will not be able to discover that you are in the visitor space.
Okay, we could talk about it. I've thought a great deal about that, about what measurement you can make that's statistical that would allow you to know unambiguously that you're seeing an effect of de Sitter space and not an effect of some mass distribution that you didn't understand.
But in fact, one of the very interesting experiments that are trying precisely to differentiate between dark energy and change of gravity are the ones which are trying to measure precisely the periodic precession of the moon. And actually they are pretty close to the...
Well, as you know, those experiments that change gravity have a much bigger effect on the precession of the moon than dark energy, right? Yeah, okay. So you could test for variations in gravity much more easily than you can test for dark energy. And that's when you know it exists, and you can measure it independently. No, you're right. Look, I'm just going to argue that there'll be maybe telltale signs, and it'd be great to look for that, but the question always is, and always will be, I would argue, do you know the mass distribution of the galaxy well enough to be able to look for deviations at the 1 part in 10 to the 6th level and argue that you can map the mass distribution well enough? Maybe you can. It's certainly clear to me right now you can. Yeah?
Let me have a go.
Good.
So in this scenario that we're discussing at the end, yes, you will see a static universe, but I think you will know that it had a beginning.
You'll have a beginning, yeah. You'll be able to calculate the age of the universe by saying how long have stars been producing helium. Because you won't know the beginning was in a Big Bang. You'll know it had a finite beginning because 60% of the universe is helium, and you'll know the rate at which stars are producing it, and you'll say the beginning of the universe was then, but you won't have any idea of what the beginning was, I would argue.
Well, okay, you're also going to be confronted with a couple of puzzles, which is the origin of matter and the nature of dark matter. And you will perform experiments which will tell you precisely what the properties of that dark matter are. So what story will you construct for where that dark matter came from?
You know, what I love about talking about this is it motivates you to think about these questions. And you're absolutely right. I mean, if you don't know, there'll be puzzles, right? The question is, will there be an observational way to resolve the puzzle? And I hope there will be, but my suspicion is, without any other evidence, is that you'll be able to come up with lots of possibilities, because you'll assume, like we assume now, that quantum gravity is the answer. Okay, you'll assume that the initial conditions are, maybe you'll assume the initial conditions are anthropic. The universes are created at random, and that, no, but I'm assuming there it'll be, because it'll be much less that's measurable. And so the A word will give it a perfect, is just as good an answer then as it does now. It will be great if you can come up with the answer. I'm just saying that the direct observational evidence will give much less motivation. Yes?
You said that there was no example in the history of science where the anthropic explanation turned out to be right and the dynamical one wrong, but that's not true. There are several examples.
Give me an example.
Do you want examples?
Yeah, of course.
Okay, so, but that's not the question.
Huh? But if you say it, if you say it, you should still... Okay.
So, well, one example obviously would be the Kepler theory theory of the planets. One is
The what?
The Kepler theory of the planets based on symmetry, which turned out to be wrong, while the anthropic explanation was correct. The other one would be the large number hypothesis of Dirac, which turned out to be wrong, and the explanation again was just anthropic. So what I want to say is that, so in science there are. Why we don't know them? It's just simply that science obviously correctly wants to find fundamental explanations. So when you find out that actually your answer was an anthropic one, you decide that it was a wrong question to ask, and you set it aside and you go for another question. Same thing could be for the cosmological constant. And maybe our question that we thought was a fundamental one actually was not. It's just an environmental explanation. This does not mean the end of science. It just means that we've been asking the wrong question. We should be smarter and ask a better one.
Well, maybe, yeah, maybe. But on the other hand,
The machine doesn't work in November. We have many things to think about.
no, I mean, yeah, the point. The point is, will we be able to determine the answer to that question, whether it's anthropic? And I would challenge you to say that any of those so-called anthropic explanations are not explanations at all. That every time we understood things, we understood we had Newtonian gravity that explained the orbits of the planets. When we talk about the other major, the large number hypothesis, we think it hasn't explained anything yet. It's an interesting hypothesis. It hasn't been an explanation of anything. It certainly doesn't. It's consistent with why gravity is much weaker than electromagnetism. But no one in this room has stopped thinking about explanations of why gravity might be much weaker than electromagnetism. The best example I know of is the one I alluded to, which is people argued that, look, if you don't have this resonance in stars, you won't have helium come together and produce carbon. So maybe nuclear levels are just random. And they're randomly determined, and our universe, we happen to live in one where there's this resonance, so you can form carbon. But then, happily, we came up with a theory called quantum chromodynamics, which is a fundamental theory that, in principle, allows you to calculate nuclear resonances. And so, every other time that people have given and thrown up their hands and say there's no fundamental way of calculating everything, people have found a fundamental way of calculating things. Now, that, as I say, that doesn't mean it's going to continue, and this may be an example of the end.
Hello. I know some people that is trying to establish some links between quantum information theory and cosmology. What do you think about this approach?
Well, actually, I've been studying that. And let me close with something that sounds like science fiction, but I think is really, it may be science fiction, but it's kind of fascinating to me. If we live in a universe dominated by a cosmological constant, then you can actually show that there are a finite number of processes, there's a finite number of bits in the entire future history of the universe that you could process, because there's a Hawking temperature. We've calculated that number. It's 10 to the 120. And the amazing thing is, by the way, that if you calculate the amount of information the universe could have processed from the beginning of the time to now, it's 10 to the 120 bits. So we happen to, again, for some weird reason, living right in the middle. Okay? If you like those coincidences. But here's something fascinating. Take Moore's law and ask how long it would take before you can process all the bits that all the available energy in the universe allows you to process. It's about 200 years. Of course, yeah, I mean, because an exponential is e to the 200 is a big number. But that's kind of fascinating to me, because it suggests that civilizations like our own that are currently powered by exponential increases in information processing can only exist in that way for a period of a few centuries. And that may be relevant for SETI and for thinking about how we look for, because it may be that civilizations, if they last for billions of years longer, they're limited. They'll be limited in their processing by the available energy of the universe. And maybe that is science fiction. Anyway, thank you.
Thank you very much, Lawrence.
Okay.